Hello, everyone. Before we start the lesson, let's take a look at an interesting story to understand piezoelectric effect. To date, over 100 singing sand phenomena have been discovered worldwide, including the Mingsha Mountain in Dunhuang, Gansu, and the Imkan Singing Sand Bay in Ordos, Inner Mongolia. The sand's sound is not a mystery. Due to the uniform mechanical composition of the sand grains, which contain a high amount of quartz, when pressure is applied under dry and windless conditions, an electrical charge is generated on their surfaces. In mineralogy, this property is known as piezoelectric effect. The contraction and expansion of piezoelectric crystals produce sounds. This is the origin of the singing sand phenomenon and also a vivid manifestation of piezoelectric effect in everyday life. In this lesson, we will learn about the meaning of piezoelectric effect and the commonly used materials. First, let's learn about piezoelectric effect. Piezoelectric effect is a phenomenon where certain materials, when subjected to an external force along a particular direction, deform and become polarized internally. This causes opposite charges to appear on the two surfaces of the material. When the external force is removed, the material returns to its uncharged state. If the direction of the applied force changes, the polarity of the charges also changes. This conversion of mechanical energy into electrical energy is known as the positive piezoelectric effect or cispiezoelectric effect. Conversely, when an electric field is applied along the polarization direction of certain materials, they undergo mechanical deformation or stress in a specific direction. When the external electric field is removed, the deformation or stress disappear. This conversion of electrical energy into mechanical energy is known as the inverse piezoelectric effect or the electrostriction effect. First, let's learn about piezoelectric effect. 1. Piezoelectric effect of quartz crystals. When quartz crystals are not subjected to an external force, no charges are produced on their surfaces, and they are neutral overall. The structure of natural quartz crystals is represented by three mutually perpendicular axes in crystallography, Z, X, and Y, which denote their coordinates. The Z-axis is the optical axis, which is the crystal symmetry axis. The X-axis is the electric axis, where the piezoelectric effect is most pronounced, meaning that charges generated by the piezoelectric effect are generally distributed on planes perpendicular to the X-axis. The Y-axis is the mechanical axis, along which mechanical deformation typically occurs. When the quartz crystal is subjected to pressure along the X-axis, it undergoes compressive deformation, and the relative positions of positive and negative ions change, so the centers of positive and negative charges no longer coincide. The electric dipole moments component along the X-axis, P1 plus P2 plus P3, is greater than 0, resulting in the appearance of positive charges on the crystal surface in the positive direction of the X-axis, whereas the components along the Y-axis and Z-axis are 0, hence no charges appear on the surfaces perpendicular to the Y-axis and Z-axis. This phenomenon of applying force along the X-axis and generating charges on the crystal surface perpendicular to the X-axis is known as the longitudinal piezoelectric effect. Similarly, when the quartz crystal is subjected to pressure along the Y-axis, negative charges appear on the crystal surface in the positive direction of the X-axis. The components along the Y-axis and Z-axis are 0, so no charges appear on the surfaces perpendicular to the Y-axis and Z-axis. This phenomenon of applying force along the Y-axis and generating charges on the crystal surface perpendicular to the X-axis is known as the transverse piezoelectric effect. When the crystal is subjected to force along the z-axis, whether compression or tension, the centers of positive and negative charges remain aligned, so applying force along the optical axis does not produce a piezoelectric effect. 2. Piezoelectric effect of piezoceramics. Piezoceramics are artificially made polycrystalline piezoelectric materials. In the absence of an external electric field, the electric domains within the crystal are randomly distributed, and their polarization effects cancel each other out, resulting in zero polarization intensity inside the piezoceramics. So the original state of piezoceramics is neutral and does not exhibit piezoelectric properties. When an external electric field is applied to the ceramic, the polarization direction of the electric domains rotates and tends to align with the direction of the external electric field, thereby polarizing the material. The stronger the external electric field, the more electric domains will fully reorient towards its direction. After polarization treatment, a strong residual polarization remains within the ceramic, resulting in changes in polarization charges on planes perpendicular to the polarization direction. This phenomenon, where mechanical stress is converted into electrical effects due to force, transforming mechanical energy into electrical energy, represents the positive piezoelectric effect of piezoceramics. The magnitude of the charge is directly proportional to the applied force. The piezoelectric coefficient of piezoceramics is much larger than that of quartz crystals, which is why piezoelectric sensors made from piezoceramics have higher sensitivity. The earliest used piezoceramic material is barium titanate. Its piezoelectric coefficient is about 50 times that of quartz, but it does not match quartz in terms of temperature stability and mechanical strength. Let's conclude our lesson. We mainly learned about the meaning of the piezoelectric effect and the piezoelectric effects in two common materials. You can review some materials after class to learn about the applications of the piezoelectric effect and prepare for the next lesson. That's all for this lesson. See you.